All right. It is, again, Tuesday evening, and we're here to do some chemistry. So kind of like Tuesdays. It's kind of nice to do this in the evenings here. So if you're here, oh, my phone's ringing. If you're here, go ahead and drop your name in the chat. Say hello, just so I know who's around. It looks like we've got a bunch of folks here tonight, so this should be pretty good. So redox reactions, right? They are quite challenging for students. And so if you've already had them in class, you'll get it a little stronger, help you really sink that into your brain. And if you haven't, then when it comes up, you'll be ready to go. So let me show you what we're doing here tonight. Find it over here. There we go. All right. So these are the questions that we're going to work with tonight. And they're all centering around the idea of redox reactions. And so these are the types of things you're going to see on exams as you go forward in chemistry. So we'll do some oxidation numbers, some redox, different kind of half reaction stuff, and so on. So let's do that. But before we do that, let's see what we got. Looks like Fran is there, Len is there. Excellent. Welcome, everyone. Last week, we did a reaction where we were trying to get 3 layers of different chemicals, different precipitates, and it didn't come across as clean as we would have liked on the video. We could see it, but this is what we ended up with, which I thought was pretty cool. This one here, we have, that looks like iron 3 hydroxide, copper 2 hydroxide, and magnesium hydroxide. So we did 3 layers of precipitates here. So kind of fun to see that. I think there's a video linked from the description of this stream here if you want to watch the video of me making that. All right. Just Fran and Len are here? Nobody else? Jason's not here? All right. So let's do this. I'm going to show you how to do one, and then you can do them. All right. Let me make it a little bigger here so you can see it. So when we're looking at redox reactions, the first thing you've got to do is you've got to find the oxidation numbers. If you can't do that, then it's kind of all over. So if you're given something like this, here we have a negative charge. So this is an ion here. For ions, everything adds up to this charge here. So all of these numbers here, they'll add up to that 2 minus. And we know that oxygen itself is going to be minus 2. So you could say that that's X minus 2 times 4 oxygens equals that negative 2. X minus 8 equals negative 2. Add 8 to both sides. X would equal a positive 6. So with redox, if you just follow these rules here, you can always figure it out. This is as hard as it gets. This is the hardest thing that you'll see. So if it's neutral, everything adds up to 0. If it's an ion, it adds up to the charge. So give it a try. See if you can do oxygen, sulfur dioxide, and magnesium oxide. Oxygen should be pretty easy if you look at the rules. Give you a hint here on oxygen. So when you're doing redox, if you have what's called a free element, that's like Na, Fe, H2, O2, S8, it's always going to be 0. So the oxidation number on each oxygen, that's going to be 0 for you. For the next one, for the SO2, oxygen is negative 2. And you've got 2 of them. So this has to be, well, 2 times negative 2 is negative 4. This has to be plus 4, because all of those have to add up to 0. Hello, Isha. Welcome to our stream here. And then for the last one, this one's a kind of hard one. So we know that oxygen is always negative 2. We know that all of this adds up to this negative 1. X minus 2, 4 oxygens, equals -1. X minus 8 equals a -1. Add 8 to both sides, plus 7. So this is plus 7 here. So the key to oxidation numbers, these rules here, if you know these rules, there's like one or two other little rules, but these are the key rules here. If you know these, you're going to be good. There's a link in the description to a video where they have these rules. I have the rules and lots of practice. If you can't do this, you can't do redox reactions. It really mess you up. All right, well, let's go down and try something else. Which one of these is redox? Which one, or ones, I should say. There could be more than one. So the key to redox is the numbers change. So did the numbers change? Went to +4 here. And oxygen did not change, but sulfur +4 to +6. So this is a redox reaction. What about this one here, though? If they change, it's redox. And the bottom one? Silver's +1, +1. Nitrogen +5, +5. Oxygen -2, -2. Na +1. Chlorine -1. Yeah, so this is not a redox reaction. It's a double displacement reaction. And double displacements are never going to be redox. Non-redox number 3. There's Jason. That's one where you're at. And Wada, welcome. And Slade is here. Got a lot of folks. Excellent. All right, so you should be able to do oxidation numbers because then you can tell if you have a redox reaction. So that's not too bad. Let's do our demo. Let's look at this and then we'll do a demo because demos are always interesting. So this is a redox reaction, and if I wrote in the oxidation numbers, this is the ionic charge, which is different but overlaps. So 2 plus, 3 plus. Oxidation has the plus after the number, and 0. You can see it's redox. So the aluminum, Al, goes to Al 3 plus. And the only way it can get to Al 3 plus is these have to be equal in terms of their charge. We need 3 negative charges. So we put 3 electrons. 3 times 1 minus 3 plus. So that's 0, that's 0. Over here goes to Cu. So the only way we can balance this is put 2 electrons here. And those are the half reactions. So that's pretty simple. But what you really want to understand is these electrons here, they're the same electrons. This isn't balanced, but the aluminum loses the electrons and the copper gets them. So let's see if we can do this actually as a reaction. I'm going to jump over to my little cam here. There we go. So these are my watch glasses. And I'm going to take some aluminum foil here. Here's my aluminum foil. And I kind of make a little dish of it here. So we make a little bowl of aluminum foil. And we're going to put copper 2 sulfate in there with it. So remember, we said that the aluminum is going to give electrons to the copper. And if copper goes from copper 2 plus to Cu, it should be a solid. So we should start seeing, that wasn't supposed to happen, but that's okay. We should start seeing copper in a minute. That blue color that you're seeing right now, those are the copper 2 ions. And you're starting to see a little darkness at the bottom. That's the copper actually forming. Half reactions aren't always between metals, Jason. You can have half reactions between certain nonmetals, like CH4 plus O2 combustion. that would be a redox reaction. So you'd have half reactions there too. So check this out right here. The dark there is copper coming out of the blue solution, and then the aluminum is dissolving. It's becoming Al3+, so it's going into the water. So after a little while, the blue goes away, and you're left with just the kind of copper metal sitting there, and there should be a hole in the aluminum. Let's see what we got here. And these chemicals are pretty safe chemicals. I'm not worried about them doing anything. If I get them on me, I'll just wash my hands off. So I don't know if you can see that clearly. You're starting to see kind of a copper color, and all of the blue is gone in that aluminum there. So that's our redox reaction, and we'll let that go for a minute. I'll put a little more in here. It'll eat a hole right through the aluminum. There'll just be like a big hole in the aluminum. There may already be. Not yet. We'll come back to it. All right. Let's go back. So copper 2 sulfate, this is the solution right here I'm using. It's pretty safe stuff, but it does a lot of neat stuff because it has that Cu2+ in it. That's what makes it that nice blue there. One of my favorite chemicals. All right, so let's go back to the screen here, and you're right, Jason, it's non-iodized Cu. It's solid copper. It's like on a penny here in the US we have copper on it. Yeah, it doesn't look as shiny, but it's just copper metal. And the aluminum, that just goes away, dissolves into the solution. So if you guys are doing these redox reactions here, writing half reactions, you could then balance the half reactions. So let me get this out of here. You could take and multiply this side by 2 and this side by 3, because 2 times 3 is 6 electrons. 3 times 2 would give you 6 electrons. So it's kind of like if you do it to both sides, it's fine. We're kind of equalizing or normalizing these equations. So that's how you would balance those. And then you go through the rest of the redox balancing. But I don't want to get into that too much tonight because that might make your brains explode. It might not. So see if you can do this. See if you can write the half reactions for this. And the key is we kind of ignore, we don't worry about the oxygens too much. We're really worried about these species here. Give it just a little initial try so your brain struggled with its sub. Hello, N-Beatify. Nice to see you. Excellent. Half reactions. So I'm going to start out, give you the first part. And then here you would have SO3 2- goes to something. So really, this here will go over here. We're interested in the manganese, but we have to keep the oxygens there. And then we have SO4 2-. So these are the half reactions. They're not balanced. We have different oxygens and we have different charges, but this is where it gets complicated because you can't just look and add electrons because you have all these oxygens. So if you were actually balancing this as a half reaction, you would balance the oxygens. You have 2 here and 4 here. You'd add H2O. That would give you 2 oxygens, but then you'd have hydrogens. So 4 hydrogens, you'd add H+. So it's kind of a big process. And only then could you figure out how many electrons you needed. So I'm building a guide on how to balance these half reactions here. And if you would like to get an advanced copy of the guide and give me some feedback on things that are right and wrong or helpful, that would really help me. So I'm going to put this link. It's a Google form. And if you just put your name and your email, when I have the guide done, I'll share it with you and you can give me feedback on, is it good, what needs fixed, and then we'll release it to the whole world after a little bit. So how do the charges change, like on the oxidation numbers? I think Norm is asking. Really what's happening with redox is we're exchanging electrons. So manganese went from +7 to +4. So it looks like it gained electrons because it got smaller. +7 to +4 means you got smaller, you're reduced. So, and it got those electrons from the sulfur. When we go to balance all of the equation here, we can then account for the numbers and make sure the ratios are right. But I would say like a problem like this would take me 5 minutes or longer to explain. There are links. There's actually a link to this specific problem in the description for this video if you want to see the whole process. And that's what the guide's all about, is how to do the whole process. I hope that helped. Okay, half reactions. Let's talk a little bit about, let's go back and see our demo here. What's happening? Oh yeah, check it out. This is all copper. The red is, oh, it ate a hole in the aluminum, and underneath you can see that's the copper. There's still a little blue in the liquid. That means there's some copper 2 ions, but the red, that's all copper, and the aluminum that's gone, that's dissolved in the liquid. So we still have those aluminum atoms. They're just ions, Al3+. That's pretty cool. Let's do that again. Let's take a big piece of this here. So that's the danger when you're a chemist and you have the chemicals here at home. They're fun to play with. So I'm going to make a little boat here. And we're going to fill the boat with, I actually have to put some salt, some NaCl, just to get it started, because the aluminum's covered with aluminum oxide. So it's kind of like a catalyst. It doesn't react, but you need it there. In the chaser, that copper is solid, but it's kind of like in the liquid, so it's a little bit kind of fluffy. But I could get the solid copper out of here, out of this. I could take this solid copper here and get it out. Like you can see, look, it's like a chunk of it right there. And I could like make that into something, copper, like, I don't know, a penny. Yeah, what the NaCl does, Jason, is it kind of pokes a little hole in the aluminum so that the copper 2 sulfate can get through to it. Let's dump a bunch of this in here and see what happens. We may have to wait. It is a pretty quick reaction, though. Like, I can see here that instantly there's a little bit of a color change. If you do this with copper 2 chloride, it can get so hot the water starts to boil. So I decided not to do that tonight. All right, so we're going to let that one cook for a little while, see what happens with it. But you can see it getting darker already. I'm pretty pleased with this. I thought this was kind of nice, the big hole. All right, so here is a question for you that you need to be able to do for your tests and so on, is tell what type of reactions you have. Yeah, Chaser, and the copper 2 sulfate, they sell like at hardware stores. People put it into their pipes to kill roots sometimes. So kind of a neat experiment. So give this a try. What type of reactions do we have? And kind of, it is a bit of a giveaway here because we have 2 things here and 1 thing here, and then 1, 2. So you could also tell if you have a redox reaction as well. One of these is redox, 1 isn't. You could figure that out too. So in the first one, like Jason, you're saying, the copper pushes the silver out. So now we have silver all by itself. So this is a single displacement reaction. I'm going to run out of room. Single displacement, and the oxidation numbers do change, so it's also redox. This one down here, these guys here switch places. So the magnesium's now with the hydroxide, the sodium's now with the chloride. So this is a double. You can see how they shift places. This is not redox though. So whenever you have a double displacement reaction, it will not be redox. But when you have a single displacement, it will be redox. So just kind of a good thing to be aware of. All right, so let's go. We're at number 5. We're going to do 2 more, and then that may be kind of it for me tonight. What's happening over here in our beaker? So it's kind of interesting. Looks like it got a hole in it already, and all the copper stuff is at the bottom. And if I put enough copper 2 sulfate in here, I could just dissolve the aluminum. It would all be gone. I'll put some more in here. I'm going to let it just kind of cook a little bit. If I'd started this like immediately, we could have dissolved the entire aluminum. All right. So give this a try. What is oxidized and what is reduced? And you probably have seen this before. Leo the lion goes grr. What is oxidized and what is reduced? Hey Wada, it's good to see you there. I was wondering if you were around. So aluminum goes from 0 to +3. We won't worry about the coefficients. Chlorine goes from 0 to -1. So these are free elements, right? So they'll be 0, and we can figure this out. If you had the rules in front of you, you could figure that out. The way I do this is I see it goes from 0 to -1, so that got smaller. That has to be reduced. I can't spell it, reduced, because the number got smaller, right? Here it got bigger. We say that's going to be oxidized. So if you need to remember how to do it, write the oxidation numbers, and the one that gets smaller, 0 to -1, 1 minus, it should actually be -1. When you write ionic charge, the sign goes after. When you write oxidation number, the sign goes before. But anyways, 0 to -1, I know that the number got smaller, the number was reduced. So the chlorine is reduced. That means the aluminum is oxidized. And typically metals are going to be oxidized. Yeah, Chaser, if you look at the description to this, I'm working on a guide right now, so unfortunately my guide's going to take a few weeks to get out. But if you sign up from that link I put there, you can be the first to test my guide and tell me what needs fixed and so on. I'll put the link back in case you missed it. All right, so we got it. We got aluminum, the metal. Typically the metal's oxidized. The non-metal typically is reduced. And I got one more. What time is it here? Oh, it's getting late. Later. How about this? What is the oxidizing agent and the reducing agent? And if you're dyslexic, this will just mess with you. I have a touch of that myself, and I always get confused with this. Thanks, Chaser. Excellent. Good to have you on the list for the guide. So remember I said that if the sign is after the number, this is ionic charge, but for these ions, it's the same as oxidation number. So these are going to be the oxidation number here. Whoa. All right. So I can just look at this here, and I know that that's the oxidation number on each chromium. So after a while, you just kind of remember it. Like, this is real common. So take a look. What's oxidizing agent and what's reduced? So we went from +6 to +3. Number got smaller, so this is reduced. And here, we went from +2 to +3. It got bigger, so we're oxidized. D-I-Z-E-D. And so, Jason, you were talking about metals and nonmetals, right? Here we have a metal being reduced and another metal being oxidized, so that can happen too. So if chromium is reduced, it's reduced because it got electrons from the iron here. So iron reduced it, so iron is the reducing agent, and it looks like the iron lost electrons, the chromium took the electrons, so it is the oxidizing. I'm having trouble spelling words, so I know it's getting late. Chromium is always kind of an exception in a lot of ways, electron configurations, Jason, and other stuff like that too. So that's kind of it. I do want to wrap up with one thing, though, that I think is kind of real important as we look at this, is why these rules. See if we can find it. Where are our rules at? Why are these rules for oxidation numbers? Like, where do they come from? Because you're told to learn all this stuff, but where did it come from? And when I learned where it came from as a student, I was like, oh, okay, that makes sense. So here's the deal. When you're talking about oxidation numbers, it's all based on electronegativity. So the more electronegative element is going to get the electrons. So if we look at this rule right here, fluorine is always -1. Fluorine's the most electronegative, so it'll always get an electron from other substances. So fluorine has 7 valence electrons, so it only needs 1. So it'll always just take 1. Oxygen, that's -2. That's because it has 6 valence electrons. It needs 2 more. Oxygen will always take 2, and it's very electronegative, pretty much from everything except fluorine, because fluorine's more electronegative. So these rules are all based on electronegativity. The more electronegative element, that gets the electrons transferred to it. So that's where that's all kind of coming out of. I didn't realize that or understand that till I started teaching. So you guys are going to be way ahead of where I was at when I was starting to learn this stuff. So that is it. I'm going to put the link one more time to my form for testers if it's still on my clipboard. No, it's not on my clipboard. And if you want to get my Redox guide, the first version where you can check it out and help me make sure it's really good, maybe I'll put your names in it when I finish it. Join that link up there somewhere to that Google form. And then we're back Thursday. I'm not quite sure what we're doing. Maybe I'll find another demo, because our demo tonight, I would say, was pretty successful. I think we, yeah, I call that pretty successful there. And there's all that copper there at the bottom. Maybe I'll go make a penny or something. All right, I'll stick around in the chat for a few minutes here when we're done, but I'm going to end the stream and hopefully see everyone on Thursday. This is Dr. B, and as always, thanks for watching.